Welcome back to Mr. DuPage's classroom. This lesson is for my Algebra 1 class. It is 8.7, Exponential Growth and Decay. Before we actually get into the lesson, let's take a look at a mathematical investigation. All right. What we're going to investigate is, could vampires actually exist? So let's read our little paragraph here. Let's assume there is one vampire to start. On the first night, this first vampire, Count Dracula, I guess, bites two people, creating two vampires. Then on the second night, Dracula and his two new vampires each bite two more victims, creating two more vampires each. The third night, each vampire, including Dracula, bites two more people, and so on. Let's set up a chart to explain the situation. From there, we'll create a function that represents this situation. Finally, we will use our function to estimate for future numbers of vampires. All right, so on night 0, this is before Dracula ever bites anyone. He's the only vampire, right? So the question is, how many vampires are there? Well, there's one. So the pattern at this point is, how do I get one? Well, it just happens to be one person. We'll talk about the exponent here in 1 second. Okay? After the first night, when Dracula goes out and bites two people, how many vampires are there? Well, there's 3. So how did I get from 1 to 3 using multiplication? I would have taken 1 times 3. Well, if you remember from our exponents, that means that I had 3 to the first power. But we also multiplied by 1. So my exponent, how I would write that, is 1 times 3 to the first power. Okay? After night 2, everyone went out and bit 2 more people. So now I would have 9 vampires, which means I would have 1 times 3 times 3, which means my exponent is 1 times 3 to the second power. What about the third night? Well, I'm going to have 27 after everyone goes out and bites 2 more people. So it would be 1 times 3 times 3 times 3, which is 1 times 3 to the third power. After the fourth night, I'm going to have, well, 1 times 3 times 3 times 3 times 3. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So I have 1 times 3 to the fourth power. So we've gone from night 0, where I had just one vampire, which is Count Dracula, I guess. In only 4 nights, he was able to create 81 vampires. Okay? So that's a little bit of a scary situation, but let's continue to see what happens after night 10. Okay? After night 10, I have 1 times 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, let's write that as an exponent because that would be a little easier to type into our calculator. If you notice, every night is my power. So I'm going to have 1 times 3 to the 10th power. If you type in 1 times 3 to the 10th power exactly the way it looks, you'll end up with 59,049 vampires. Okay? So again, after only 10 nights, one vampire, if everyone bites 2 every night, one vampire can turn into 59,049 vampires in only 10 nights. Okay? So what if it was to the nth? We're talking about to the nth. That means that we don't know how many nights it would be. What we would do is we would take 3 to the nth power. Our exponent would be 1 times 3 to the nth power. I can't write that as my extended form because I don't know how many nights we're talking about at this point. So what is the pattern? Well, we start with one vampire, and we multiply by 3 every night. Okay? So the function that I could write is y equals, or f of x equals, depending on how you want to look at that, y equals f of x equals, it would be 1 times 3 raised to, depending on how many nights we have, so the x or the nth, whatever we want to say. What our function is y is going to equal our exponent column. Okay? So let's take a look at some of the questions that they have for us here. How many vampires would there be after the 10th night? Well, we already figured out the 10th night. The 10th night would have been equal to this 59,049. So there would be 59,000 vampires. Now it wants to know how many vampires after the 18th night. Well, how can I set that up? Remember, it's always 1 times 3 raised to some x, which in this case would be the 18th. If I have 1 times 3 to the 18th, I would end up with 387, 420, 489. 387,420,489 vampires. So in only 18 nights, we went from 1 to 387,420,489 vampires. So the question now is, how many nights would it be until the entire world's population was vampires? Assume the world population is 7 billion. All right, so all we're going to do here real quick is we're going to guess and check. So since we know that after the 18th night we have not hit 7 billion, why don't we check the 19th night? Well, how do I do that? I'm going to take 1 times 3 to the 19th, which would get me, haven't actually typed that through my calculator yet. 3. That would get me 116, 226, 1467. That would get me 1,162,261,467. So I've jumped from only right around 400 million vampires to over 1 billion in one more night. That didn't quite get us to 7 billion, so let's try night 20. On night 20, I would have 3, 486, 784, 401. So I have 3,486,784,401 vampires after night 20, which means I still haven't quite made it to 7 billion. Let's try the last one, or another one, I should say. Night 21. So after night 21, I would have 10, 460, 353, 203. So if there were enough people on the planet, there would be 10,460,353,203 people after just 21 nights. So when would the entire world's population be vampires? It would be sometime during the 21st night. So if vampirism actually worked by just getting bit and then you become a vampire and you are required to drink blood, and in this case you're required to drink blood every night, it would not take very long for the entire world's population to become vampires. So could vampires actually exist? In this study, no, they could not, because they would have to drink blood, and a bite turns that other person into a vampire. All right? So let's look and see what we actually learned here. That is what is known as exponential growth. Notice that it did not grow at a constant rate. It actually went up. It jumped quite a bit every day. Okay? Let's do a review real quick about a line. What is the equation for a line, the slope-intercept form? Well, it's mx plus b, where m is slope, b is the y-intercept. To graph it, we start at the y-intercept, move by the slope. Hopefully at this point, you all know how to graph, and we really don't have to worry about that too much. Well, for exponential growth and decay, actually, there is a formula just like for a line. And in the exponential growth formula, which is y equals a times b raised to the x, or if you wanted to, put parentheses around the b, a represents the initial value. If you remember from our Initial value or initial amount. If you remember from our vampire story, the initial amount was 1. That's why it was always 1 times 3. B represents the growth rate. Well, we grew by 3 vampires a night, so our growth rate was 3. So it was 1 times 3 raised to the x. Our x is the amount of time. Okay? So the x in that case is the amount of time. So if b is greater than or equal to, I don't know why that's not in there, but greater than or equal to 1, then we have exponential growth. If b is less than 1, my growth rate, remember what's inside the parentheses, if it's less than 1, which means it'll be a decimal that is smaller than 1, so 0.9999 or under, if we have less than 1, then it'll be exponential decay. So if what's inside the parentheses is 1 or greater, it's growth. If it's less than 1, then it is decay. Okay? So now we need to evaluate each exponential function. So for y equals 4 times 3 raised to the x value, I'm going to put negative 3 in for x. So for y equals 4 times 3 raised to the negative third. Remember, I can make that 3 just in parentheses. Means the same thing. Now, from our exponent unit that we just finished, if I have a negative exponent, what's going to happen is I'm going to have 4 times 1 over 3 to the third. Since it was a negative exponent, I had to move it down through my fraction bar. It gets rid of the negative for us. So then I have 4 times 1 over 27, which is really 4 over 27. Notice that my number started at 4 and it got smaller at the end, right? Because I had a negative exponent, okay? Which turned my b value into a fraction, which is less than 1, right? So y equals 4 times 3 raised to the 6th. Well, here, what's going to happen is it's going to be growth because my b value is greater than 1. I don't have a negative exponent to flip it and make it less than 1. So it would take 3 raised to the 6th power. 3 raised to the 6th power is 729. So I'll have 4 times 729, which is equal to 2,916. So now you've seen an exponential growth problem and an exponential decay problem, and we're good from there. So part B, I'm going to put negative 2 in for x. So I have y equals 5 raised to the negative second, which is really 1 over 5 to the second, which is 1 over 25. For negative 1, I would 5 raised to the negative first, 1 over 5 to the negative first, which is really, not negative first, I'm sorry. Once I flip it, that exponent turns positive, so it's 1 over 5. Then I have y, 5 raised to the 0 power, which is, as we know, just 1. Then I have y equals, I'm going to put 3 in for x, 5 raised to the third, which is 125. And then finally, I'm going to put 5 in for x. So 5 raised to the 5th would get me 3,125. Okay? So if you ever have a problem that asks for to evaluate our equation for a domain, what that means is you just put each one of those numbers in for x and go ahead and solve. Part C, we have a story problem. Suppose 10 animals are taken to an island. Before we even continue, what is our formula? Y equals A times B raised to the x. A is our initial value, B is our growth rate, X is our time. So suppose 10 animals are taken to an island, and then the population of these animals quadruples every year. Before we even continue, let's start plugging things in. Well, A is our initial value. What is our initial value? Well, the 10 animals. B is our growth rate. That comes from the word quadruples. Quad means 4, so we're going to multiply by 4 every year. Okay? My growth rate is 4 every year. Write an exponential function that represents this situation. When it asks you that without giving you a year, a number of years, it wants you to just put x in for the time. After that, now it says, and determine the number of animals there will be after 6 years. So it would be y equals 10 times 4 raised to the 6th. 10 times 4 raised to the 6th. If we type that straight through on our calculator, you're going to end up with 40,960 animals after only 6 years, if obviously nothing is killing them off. So that's why, I don't know if any of you know what Asian carp are, but that is why they are overrunning the rivers in Illinois, because there's nothing to kill them. They are growing at an exponential rate, and that's why they're overrunning everything. Okay? Let's look at the back. Graph each exponential function. We're going to do the same thing with our table that we did when it asked us to evaluate once it gives us domains. So what I'm going to do is, for x is -2, I'm going to take this equation, so y equals 1 times 3 to the -2nd, and I'm going to solve for my y, which means I have to evaluate that equation. 1 times 3, so it would be 1 times, I have 3 is raised to a negative, so it would be 1 over 3. My number turns to 2, which means I have 1 over 9. Okay? For -1, it would be y equals 1 times 3 to the -1st, which is 1 times 1/3, which again is 1/3. For 0, y equals 1 times 3 to the 0 power, which we all know is 1. And for 1, y equals 1 times 3 to the 1st power. Well, 3 to the 1st power is 3, so 1 times 3 will get me 3. If you're curious where I'm getting all these numbers, they're right here, and I'm just plugging them in for x in this equation. So y equals 1 times 3 to the 2nd. 3 to the 2nd is 9, and we are good, right? At this point, now that I have my table filled out, what I'm going to do is just go ahead and graph these points. So I'm going to find -2, which is right here. I'm going to do my best to find 1/9, which is going to be really low. Don't put it on right on top of the x-axis. Like, don't do this, where it's right on top of the x-axis. Make sure that it's sitting a little bit higher than the x-axis. The bottom of it can be touching the x-axis, that's okay, but make sure it's just a little bit up off. Then we want to go about 1/3 of the way up our box. For 0, it would be 1. For 1, it would be 3. And for 2, it would be 9, which actually takes us off our graph. As you can see, it's climbing extremely quickly. That is what happens when you have exponential growth. Then I just go ahead and connect my points with a little bit of an arc, and I am done. Okay? Because my base, or my growth rate of 3 is larger than 1, we have exponential growth. Let's check part B. My growth rate is 1 over 3, which means I now have exponential decay. So if I put -2 in for x, I'm going to have y equals 2 times 1 over 3 raised to the -2nd. What that means is I have to take my 3, bring it up through the fraction bar. So I'll have 2 times 3 to the +2nd, which 3 to the 2nd is 9. 2 times 9 is 18. You can also graph these points as you go if you would like. So -2 is here, 18 is there, so there is our first point. If I put -1 in for x, y equals 2 times 1 over 3 to the -1st, which means I need to bring the 3 through my fraction bar. So 2 times 3 to the 1st, well, 3 to the 1st is just 3. 2 times 3 is 6. So when I have -1, I go up to 6. Now I'm going to put 0 in for x, so y equals 2 times 1 over 3 raised to the 0 power. Well, that would be 1. Anything raised to the 0 power is 1. 2 times 1 is 2. So at 0, my y is 2. If I go ahead and work with 1 in for my x, y equals 2 times 1 over 3 raised to the 1st. Well, anything raised to the first power is just itself. So 2 times 1 over 3 would be 2 over 3, which 2/3 is pretty close to the top of our little box there. And then for 2, y equals 2 times 1 over 3 raised to the second. Remember, I'm going to take the 1 raised to the second. If I take the 1 raised to the second, it's still going to be 1. I'm going to take 3 and raise to the second, which is 9. 2 times 1 over 9 will actually get me 2 over 9. Again, this is going to be extremely difficult to graph, but I'm just going to put it to where it's sitting on top of my x-axis. Go ahead and connect my points with a little bit of an arc going. I don't want to cross my x-axis because there is no way that I can multiply by changing my exponent and making that negative or 0. So it will just get really, really close to that x-axis and go on forever and ever and ever without ever touching the x-axis or crossing the x-axis. Well, a couple things to remember here. If my, a in my equation, y equals a times b raised to the x power, my a value is the initial amount. My b value is the growth rate. And my x value is the amount of time. I know whether it's exponential growth or decay based off of my growth rate. If my growth rate is 1 or higher, then it will be exponential growth. If it is less than 1, then it will be exponential decay. If you have any questions over this note sheet, please make sure you come in and see me. Don't be confused for more than one day. If you're confused already, please make sure you come in and get some help. Let's get you started in the new unit correctly. All right? Well, thank you very much for watching the video, and have a great day.